Closed-loop control for laser powder-based fusion can provide improved yield and reduced unit costs. Additive manufactured parts are made layer by layer. As long as layers are made correctly, the process is productive. At some point, however, a defect can be created for a wide variety of reasons. The way LPBF is performed today, the operator is not aware of the defect, and the build proceeds to completion. Final inspection is performed, and if the defect exceeds allowable limits, the part is then rejected. Using in-process inspection, however, defects are found when they are made. If the defects exceed allowable limits, the build is abandoned at that point. This eliminates or saves all the additional cost and time otherwise invested completing a scrap part. Additional efficiencies can be obtained if the defect is repairable or reworkable. Some common LPBF defects, like lack of fusion, are repairable and therefore can be salvaged by using closed-loop control. When a defect is found, a repair is performed at that time, while the defect layer is accessible. The defect is removed or restored to nominal condition. The build continues to completion. This allows a scrap part to be salvaged and converted into an acceptable part. We first developed optimum repair process conditions for lack of fusion flaws by performing several trials. 7 coupons were produced, all containing the same configuration of LOF flaws consisting of 1, 2, or 3 successive LOF flaw layers. A control coupon was made with no repair performed and was used to determine the level of porosity for each LOF flaw configuration. Each of the 6 repair coupons used a different repair process on the layers with LOF flaws. In each case, a flaw layer was first produced, followed by a second specific flaw repair process. This was performed for all flaw layers, using 6 different repair processes, one for each of the 6 repair coupons. The 6 repair processes used different combinations of laser power and powder recoating for the repair. All coupons were then CT scanned. Optimum repair processes were determined for 1, 2, and 3 layer LOF flaws based on the porosity before and after the repair was made. These optimum repair conditions were then used in the closed-loop control demonstration. A control architecture was developed to implement closed-loop control, as shown in this block diagram. The printer produces the part layer by layer. We now introduce in-process inspection, where we examine every layer after it is printed to determine if it contains a flaw or not. If we do not find a flaw, we send a signal to the print controller telling it to print the next layer in the program. However, if we do find a flaw, we then determine what type of flaw it is. We use this information to select which of the 6 repair processes to use to repair this flaw. This information is sent to the print controller and the repair is then performed. In a real system, this would be integrated with the controller and performed automatically. In the demo, the software defined the repair process to use, but a human operator issued that instruction to the printer for the initial proof of concept. A demonstration of closed-loop control was performed where we produced coupons with several types of intentional flaws and then used in-process inspection to detect these flaws. Software was used to determine what process to use for the rework, which was then used to repair the flaw. 4 coupons were produced and each one contained 6 different flaw regions, for a total of 24 flaw regions. Coupons were made with a tapering width such that the center of the taper region, that is the smallest width layer, is where the first flaw layer in a group was produced. This provided the physical fiducial mark that was later used to correlate CT data to specific layer numbers. As before, LOF flaws covering the entire layer were used. Flaws were produced as either 1, 2, or 3 flaw layers, as shown in yellow here. These flaw regions were thermally isolated from each other by 25 layers within each coupon. Flaw layers in each coupon were made in different build layers, again to eliminate thermal effects between flaws in adjacent coupons. In total, 55 LOF flaw layers were produced in the coupons in this build. CT scans were performed on all coupons to assess as-formed porosity before and after flaw repair. Tapering layer width allowed us to locate the specific layer where a flaw had been created and then repaired. The porosity in every CT slice was first segregated and then quantified using 3D CT analysis software. Lack of fusion porosity was measured before and after the repair was performed. Porosity values were extracted for every CT slice, 1 voxel thick or about 16 microns. This was plotted. Fiducial marks in the CT data were used to locate and register the flaw layers in various coupons. Mean porosity values were calculated for similar conditions. For example, the porosity for 2 different single-layer LOF flaws are plotted here, with an average value of 0.76%. Similarly, multiple values were measured and averaged for the 2-layer flaws, such as shown here. Note that the y-axis scale has changed here, as the porosity is much higher than for a single LOF layer. Porosity in the unflawed or nominal layers averaged 0.16%, which is typical of aerospace-grade LPBF parts. As expected, the greater the number of successive flaw layers created, the higher the porosity in the as-formed part, with about 14% porosity in the 3-layer flaws, shown here in red. We then produced coupons with repairs, detecting the flaws in real time using in-process inspection as previously shown. Porosity measured from CT scans of repaired coupons is shown in blue. Note that the residual porosity, or the porosity in the coupons after repair, was almost completely eliminated by the repair. When we expand the scale and compare the residual porosity in the repaired coupons with the pristine or nominal layers, the porosity level is statistically equivalent to an unflawed or nominal layer. To summarize, LOF repair processes were developed. A closed-loop control architecture was developed. LOF repairs were performed in real time with software process definition. Virtually all flaw porosity was eliminated by the repair. Rejectable parts were salvaged. Closed-loop control of LPBF was successfully demonstrated.